Theorem 1.5. Okay. Let x be a rational number whose decimal expansion terminates, then x can be represented in the form of p by q, where p and q are coprimes and the prime factorization of q is of the form 2 power n into 5 power m, where n, m are non-negative integers. Okay. Both theorem 1.5 and 1.6 are same. The statement is same, but it is placed in the reverse order. Okay. Let us see theorem 1.6. Okay. Let x is equal to p by q be a rational number such that the prime factorization of q is of the form 2 power n into 5 power m, where n comma m are non-negative integers, then x has a decimal expansion which terminates. Okay. Both these theorems is same, and they both, what they are saying is that let x be a rational number. So we know that if x be a rational number, we can express it in the form of p by q. Okay. Now we want to find the factors for the denominator q. If the factors for the denominator q is in the form of 2 power n into 5 power m, then the rational number having a decimal expansion which terminates. Okay. Now you got an idea, right? Okay. Next theorem, theorem 1.7. See, here what I am saying, let x is equal to p by q be a rational number such that the prime factorization of the q is not in the form of 2 power n into 5 power m, where n, m are non-negative integers, then x has a decimal expansion which is non-terminating or repeating or reoccurring. Okay. So by comparing these two theorems, what they are saying, x is a rational number so that we can represent in the form of p by q. If you find the prime factorization for q, if the prime factorization for the q is in the form of 2 power n into 5 power m, then the rational number has decimal expansion which terminates. If the prime factorization for the q is not in the form of 2 power n into 5 power m, then the number x has a decimal expansion which is non-terminating or repeating. Okay. For example, if I consider 7 divided by 80, see, if I find the factors for the denominator, I get 2 power 4 into 5. So in order to balance the equation, I want to multiply it with 5 power 3 on both sides. We get 7 into 5 power 3 by 2 power 4 into 5 power 4, which is equal to 10 power 4. So now it is the form of 2 power n into 5 power m. So we are getting a decimal expansion with terminating. Okay. But here, if you take 1 by 7, 7 for primes, if you are getting prime factorization for 7, we are not getting in the form of 2 power 5 into 5 power m. So it has a decimal expansion of 0.1422 something. Okay. See, exercise 1.4. Okay. Without actually performing the log division, state whether the following rational numbers will have a terminating decimal expansion or non-terminal repeating decimal expansion. Okay. Now, if you want to check whether it is a repeating decimal expansion or terminating decimal expansion, what we have to do? First, whatever the rational number they are given, we want to write it in the form of p by q. Then, for the q, we want to calculate the prime factors. If the prime factors is in the form of 2 power n into 5 power m, then we are saying that it have a terminating decimal expansion. If the prime factors for the q is not in the form of 2 power n into 5 power m, then we said that it has non-terminating repeating decimal expansion. Okay. Let us see some problems. 13 divided by 3125, which is equal to 13 divided by the prime factorization for 3125 are 5 power 5. Hence, in order to balance this equation, we need to multiply 2 power 5 on both sides. We get 13 into 2 power 5 by 2 power 5 into 5 power 5. Hence, now the denominator is in the form of 2 power n into 5 power m. Hence, it is terminating decimal expansion. Okay. Second, 7 divided by 8. We know that the prime factorization for 8 is 2 cube. In order to balance this equation, I want to multiply with 5 cube on both sides. That is 17 into 5 cube divided by 2 cube into 5 cube. This implies, it seems that denominator is in the form of 2 power n into 5 power m. Hence, it is having an terminating decimal expansion. Okay. Third problem, 64 divided by 455. I can write the prime factors for 455 as 5 into 91. The denominator, which is in the not in the form of 2 power n into 5 power m, hence it doesn't have a terminating expansion, hence it is non-terminating repeating decimal expansion. Okay. Fourth problem, 15 divided by 1600. The prime factors for 1600 are 5 square into 2 power 6. In order to balance this equation, I want to multiply 5 power 4 on both sides. This implies 15 into 5 power 4 by 2 power 6 into 5 power 6. So, when we see it is in the form of 2 power n into 5 power m, hence it has an terminating decimal expansion. Okay. Next problem, 29 divided by 343. We can clearly see that 343 is not a multiple of 215. Hence, the denominator is not in the form of 2 power n into 5 power m. Hence, it is non-terminating repeating. Okay. Next problem, 23 divided by 2 cube into 5 square. Here, in order to balance this equation, we need to multiply with 5 on both sides. Then 23 into 5 divided by 2 cube into 5 cube, which is in the form of 2 power n into 5 power m. Hence, it has a terminating decimal expansion. Okay. Seventh problem, 129 divided by 2 square into 5 power 7 into 7 power 5. See, here the denominator is in the form of 2 power n into 5 power m into something else. When it compared with 2 power n into 5 power m, it has an additional term of 7 power n. So, hence, it cannot be considered as a terminating. So, we conclude that it is not in the form of 2 power n into 5 power m. Hence, it is a non-terminating repeating decimal expansion. Okay. 8. 6 by 15. The prime factors for 15 are 3 into 5. But if you want to simplify this 6 by 15, it becomes 2 by 5. 3 2s are 6 and 3 5s are 15. So, now if you want to get prime factors for 5 in the form of 2 power n into 5 power m, we need to multiply with 2 on both sides. Then it becomes 2 into 2 by 5 into 2. So, now the denominator in the terms of 2 power 5 into 5 power m, hence it has a terminating decimal expansion. Okay. 9th, 35 divided by 50. The prime factors for 50 are 2 into 5 square. In order to balance this equation, I want to multiply with 2 on both sides. So, it becomes 35 into 2 by 2 square into 5 square. Hence, the denominator now is in the form of 2 power m into 5 power n. Hence, it has a terminating decimal expansion. Okay. 77 divided by 210. Okay. The prime factors for 210 are 2 into 5 into 3 into 7. Now, it has not in the form of 2 power 5, 2 power n into 5 power m. Why? Because it has some additional terms including 2 and 5. So, hence it is considered as non-terminating repeating decimal expansion. Okay. Second question, write down the decimal expansion of those rational numbers in question 1 above which have a terminating decimal expansion. Okay. We solved 10 problems in the previous question, in which we find 6 are having terminating decimal expansion. So, by using that rational numbers, we want to solve further. Okay. So, first one, 13 divided by 3125, which is equal to 13 divided by the prime factors of 3125 is equal to 5 power 5. In order to balance this equation, again I want to multiply it with 2 power 5 on both sides. So 13 into 2 power 5 divided by 2 power 5 into 5 power 5. Now 13 into 2 power 5, which is equal to 416, and divided by 2 power 5 into 5 power 5, which is equal to 10 power 5. So we want to make it as 0.00416. Here there is a note that whatever the power of 10 in the denominator, it indicates the digits after the decimal point in the numerator. See here 10 power 5, so it indicates 1, 2, 3, 4, 5 digits after decimal point in the numerator. Okay, right. Second, 17 divided by 8. So 8 can be represented as 2 cube in prime factors. Okay, so 17 divided by 2 cube. In order to balance this equation, I want to divide 17 into 5 cube by 2 cube into 5 cube. Now I am getting 17 into 5 cube as 2125 divided by, so 10 cube, that is 1000. So again 2125 divided by 1000, which is equal to 2.125. Third problem, 15 divided by 1600. So prime factors for 1600 are 5 square into 2 power 6. So in order to balance this equation, I want to multiply with 5 power 4 on both sides. This implies 15 into 5 power 4 by 26 into 2 power 6 into 5 power 6, which is equal to 9375 divided by 10 power 6. So if you want to get into decimal, what you have to do, we have to make 6 digits after decimal. So it becomes 0.009375. Okay. Next, 23 divided by 2 cube into 5 square. Okay. In order to balance this equation, I want to multiply with 5 on both sides. So 23 into 5 divided by 2 cube into 5 cube, which is equal to 115 divided by 1000. So this implies 0.115. Okay. Now next, 6 divided by 15. 6 divided by 15, if it's divided with 3 on both sides, so it becomes 2 by 5. If you want to balance, I want to multiply with 2 on both sides. So 2 into 2 divided by 5 into 2. So that implies 4 by 10, which is equal to 0.4. Sixth, 35 divided by 50. So the prime factorizations of 50 are 2 into 5 squared. In order to balance this equation, I want to multiply with 2 on both sides. So it becomes 35 into 2 divided by 2 square into 5 square, which is equal to 70 divided by 100, which is equal to 0.7. Okay. Now, next question. The following real numbers have a decimal expansion as given below. In each case, decide whether they are rational or not. If they are rational of the form P by Q, what could you say about the prime factor of Q? Okay. Now, what is the question given? So they are given 43.123456789. It seems like it has a decimal expansion which is terminating. So I can write this 43.123456789 divided by, I can count how many digits are there after the decimal point. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So I write 10 power 9. So for balancing this equation, I want to for balancing this equation, I am doing prime factorization for 10,000, so that it becomes 2 power 9 into 5 power 9. So it can clearly say that it is in the form of 2 power m into 5 power 2 power n into 5 power m. Hence it is called a rational number, right? Okay. Now, second problem, 0.120, 4 zeros. Since it seems like it is a repeating, it is an irrational repeating number. 3, 43.123456789, 123456789. That is, in the question it implies that 43.123456789 1 2 3 4 5 6 7 8 9 bar. So it also seems to be repeating, so it is also a irrational repeating number. Okay, note, we already seen that the relationship between the two numbers and their LCM and HCF, that is the product of two numbers which is equal to the product of their LCM and HCF. But this condition is failed when we have three numbers. So for three numbers, for finding LCM of PQR is equal to the product of three numbers, that is P into Q into R into HCF of three numbers divided by HCF of PQ, QR and PR. Again, for finding HCF, the formula is HCF of PQR is equal to the product of three numbers into LCM of three numbers divided by LCM of PQ into LCM of QR into LCM of PR.